Silicon carbide is a massive leap forward in semiconductor technology. If a standard silicon chip is a standard passenger car, a silicon carbide chip is a heavy-duty, high-temperature industrial tank. While pure silicon taps out around 100 degrees to 150 degrees centigrade, silicon carbide chips can easily operate at 200 degrees centigrade and theoretically survive up to 400 degrees centigrade or more. The reason standard silicon leaks current at high temperatures is because it doesn't take much thermal energy to knock its electrons out of place. Silicon carbide is a compound of silicon and carbon. The chemical bond between these two elements is incredibly strong. In physics terms, silicon carbide is a wide gap semiconductor. It requires roughly 3 times as much energy to knock an electron loose in silicon carbide as it does in standard silicon. Because of this, you can heat silicon carbide to extreme temperatures and it will still act like a perfect gatekeeper, blocking electricity when it is supposed to and letting it pass when commanded, with almost zero thermal leakage. Furthermore, it conducts heat almost 3 times better than pure silicon, meaning it can practically cool itself. Because silicon carbide can handle massive heat and massive voltages, it is revolutionizing power electronics. Electronic vehicles. Silicon carbide chips are used in the power inverters of high-end EVs. They can handle the massive voltages from the battery more efficiently, producing less heat and increasing the car's range. Renewable energy. Solar and wind inverters use them to convert massive amounts of power efficiently. Industrial and aerospace. They are used in environments where active cooling like fans or liquid cooling is impossible or too prone to failure. If silicon carbide is so great at handling heat, why isn't manufacturers making CPUs out of it? It comes down to manufacturing realities and the specific job of a CPU. Miniaturization, the nanometer problem. A modern CPU contains upwards of 50 billion microscopic transistors packed into a space the size of a postage stamp. We have spent 50 years perfecting the art of shrinking standard silicon transistors down to 3 nanometers. Silicon carbide is incredibly brittle, hard, nearly as hard as diamond, and very difficult to manufacture perfectly. We simply do not have the manufacturing technology to carve billions of ultra-tiny, flawless logic gates out of silicon carbide. Today, a silicon carbide chip might just be one giant transistor like a power switch rather than billions of tiny logic gates. Growing perfectly pure silicon crystals is cheap and easy, while growing perfectly pure silicon carbide crystals is a slow, incredibly expensive, high temperature process. Because it's so hard to make, silicon carbide wafers are plagued with microscopic crystal defects. If one defect lands on a CPU, the whole chip is ruined. CPUs are designed to be low voltage logic devices. They operate at around 1 volt to 1.3 volt, switching on and off billions of times a second, that is gigahertz. Silicon carbide's wide bandgap means it inherently requires higher voltages to switch on. It is designed to handle hundreds or thousands of volts. Trying to make it operate as ultra-fast, low-voltage computer memory or logic would be incredibly inefficient. In short, silicon carbide is the undisputed king of high voltage, high heat power switching, but standard silicon remains the only material we can currently carve tiny enough to do the complex math inside a computer CPU.